Hello everyone, Namaste. I am Ramnath who would like to share with you some brief analysis on what it takes to come up with a semiconductor fab in India. Everyone has seen sand, which is nothing but silicon dioxide, and its chief constituent is silicon. Silicon makes up about 27% of Earth's crust by mass, making it one of the second most abundant elements present in our planet. It comes with very useful properties such as being heat resistant, electrically conductive, and brittle. A very important aspect of silicon is it's neither a pure metal nor a pure non-metal. It is a semiconductor. It is the widely studied element in the periodic table. Coming back, the basic requirement of a semiconductor material is that it should not be a very good conductor of electricity, nor it should be a very bad conductor of electricity. Its electrical properties can be changed by adding some known impurities. Silicon is thus the most widely studied semiconductor material, and it is one of the most studied element in the periodic table. And we know that about 60% of all buildings in the world contain concrete, and in most cases concrete consists of about 30% of sand. So you can imagine how much we are using silicon in our day-to-day life. As observed, for many centuries, most of the silicon is used commercially without being separated, often with very little processing, especially in construction of buildings and roads. However, in the late 20th century to early 21st century has been described as silicon age, also known as the digital age or information age, because of the large impact that the element silicon has on the modern world economy. We know the average price of sand is about $10 per ton in the global market. However, you will observe that when it's purified further, how its worth in applications differ. You will observe that the industrial silicon is produced about 2 million tons per year, and out of that ferrosilicon, aluminum silicon alloys constitute around 45% of the 2 million tons, and 35% by the silicones and silanes, and 12% is only solar cells, and meager 3% of 2 million tons per year is by semiconductor ICs. However, if you observe, the purity of silicon in all these different segments is one aluminum alloys is 98.5, in the solar it is 99.99%, and like this in silanes, and in semiconductors it is 99.999% pure. And you will also observe that the semiconductor market share of different segments is $3 billion in silicones, and $5 billion in solar, and $6 billion in steel and aluminum alloys, and semiconductors is whopping $500 billion. It is no way close to any of these, even combined. And you will also observe these different applications where these silicon products are getting used. You will also observe that no wonder silicon is playing a vital role not only in semiconductor ICs but also in these industries as well. You know that in 2020, 1 trillion chips were manufactured in the world, and these are the several variety of places where the silicon chips went and then changed the world economy. Okay, it is not only in air force or in aerospace or in automotive applications, or in smartphone applications, or in different areas, even in healthcare, like hearing aid applications, and in pacemakers, and different places. These chips are coming in our day-to-day life and impacting the world. And you will also observe the global semiconductor market of different countries, how much they are producing and all. You will see the effect. And you will also observe that how in the coming years, how much ever we are producing, all these things are resulting into a different shortage. So you will observe that in last year, the chip shortage led global automakers to make 7.7 million fewer cars, and that resulted in around $210 billion hit to their revenues. Aside to that, even in automakers, Maruti in Indian market segment also, they have cut down the production by 60% to the normal levels in 2021 due to chip shortage. This, though, makes us understand that chip shortages will make some difficulties for the present scenario, but for the opportunistic eyes, you will understand that they are looking for some other meaningful observations. Okay, so and you will all you will also know that the semiconductor market is steadily growing, ignoring these corona years. In 2021, already we know that the production is around 500 odd billion dollars. Okay, in 2022, it will be again much higher than that. And you will know that in the semiconductor, ICs are made in these several segments, and these are the different segments, and smartphones is the largest contributor of them. And this is the forecast of 2020 to 2023. So these are the opportunistic moments which we are observing, so that how the future economy will be changed and the landscape will be changed depends on these data points. Yeah, considering one more data point of where the semiconductor manufacturing majorly happens, you will observe that TSMC market share is around 54%. It is very high compared to the next neighboring Samsung. And so you will observe that all these major countries are already UMC and TSMC are already in Taiwan, and you will observe that the total production maximum share is from Taiwan, TSMC. So there are opportunistic moments which, if one observes very closely, you will understand that there are some pockets and gaps which we can fill in over the period of time. By observing the earlier indicators on semiconductor manufacturing, we will understand that there should be some key decisions need to be made. But if we go based on the traditional empirical analysis based methods, we will meet the situation only to a certain extent. But if we go based on the advanced analytical methods, we will understand that the way of solving is first having a vision, which basically is set as $5 trillion economy by 2025 for India. So for that, there are some key critical decisions need to be made. Those critical decisions are policy reforms, infrastructure and logistic support, and these insights, we need to understand what are those insights that make these decisions. Then you will understand that the demand for goods in the semiconductor arena, inside and external, and you will also understand what are the capabilities of India, either in terms of infrastructure, in terms of finance, in terms of resources, people resource, human resource, I mean, and you will also understand that all these things, if you put together, then you will understand that you need to make what information to make these insights. Then you will understand that the social justice and equitable growth in society are to be achieved. So then when you try to achieve these things, you need to ensure some other method by which these social justice and equitable growth will be analyzed. For that you need bare necessities index on to, social indicators. So when you try to have a very good vision to move forward with good policy reforms, then you will understand that bare necessities index will improve and you will finally reach the goal Sarve Bhavantu Sukhina. Yeah, to realize the vision of $5 trillion economy in India, bold reforms have been proposed in supply chain reforms for agriculture and rational taxation system and simple and clear laws. This has changed the index of ease of doing by a great amount, and also it helped the human resource identification and increase, and also it changed several laws and rules in the financial sector. You will observe that Indian government unveiled a plan to provide incentives worth 2,30,000 crore to achieve a larger goal of making India a global electronic hub and semiconductor design, manufacturing and display fabrication units as main drivers. Aside to that, uh, it proposed and approved 76,000 crores, which is equivalent to $10 billion spread over 6 years for the development of semiconductor design, manufacturing and display fabrication ecosystem in India. So all this have made several other improvements, and they categorically mentioned that for the device manufacturers or foundries or Indian company of consortia with Indian industry partner desirous of setting up or expanding existing semiconductor fabs in India, preferably with a node size of 28 nanometer or lower, wafer size of 300 mm and a capacity of 30,000 wafer starts per month or more, then these incentives will be applied. So these are the specific and categorical modifications and incentives suggested. These are quite different to what has been proposed in the earlier years. These are all very clear, and it is also very specific about what needs to be achieved, in the sense like 28 nanometer or lower, the process node has been mentioned clearly, and in which wafer size and what are the outputs of the fab. All these things are clear, and where it needs to be ensured, and then there also it is clear that they either in the display fabrication or in the manufacturing area, all these things, any area, if we take that area, if it is improved, then the incentives will apply. To realize the vision of $5 trillion economy and also to become an electronic hub as part of it in the future, you need to understand the different segments that play a vital role in the manufacturing area. First one is the IC design area, where several fabless semiconductor companies work uh, to realize a manufacturable content. So the product which is made into a specifications will be converted through several EDA tools electronic design and automation tools by these companies by using several libraries of intellectual property data. Then the design content in specification format will be slowly converted into a manufacturable content data that will be taken by the next stage, that is manufacturing. So this manufacturing area will take this manufacturable data and take it through several phases like photolithography, ion implantation, etching, sputtering, chemical vapor deposition, all these things, and then it will make the digital content into a physical form. This is the wafer. This wafer is further taken through the next step of assembly and test, where the wafer here is taken through several procedures wherein it is cut into small dies, and which will be tested, and it will be assembled to the package, and then it will be taken and then tested and put it into a package and testing after final testing. So that is how this packaged IC will be ready for putting into the concerned application or in a system. So you will observe that IC design, manufacturing, assembly and test are the three main different items which basically start from the concept of IC from a product specification all the way up to making a packaged IC. And the integrated device manufacturing is the one which will encompass all these three stages, and pure play fab is only related to the manufacturing, and only IC design is called fabless semiconductor. Yeah, we will try to understand further how the puzzle pieces of this are positioned in the industry. If you observe that the fabless companies, that means like who just make the IC design and not the fabrication, they take the share of around 66%. And if you consider the foundry which which manufactures only the designs made by them and nothing else, they won't do the design, that one basically consumes around 21%, and packaging 2%, and manufacturing equipment, that means like whatever the equipments are needed by the foundry, that will consume around 10%. Coming to the PE ratio of these segments, you will observe that EDA, that means like the software companies which will make different electronic design automation tools for the fabless semiconductor company or for the foundry, will basically have the PE ratio of 43.8, and the fabless is the next one, which will be 32, and equipment is 24, foundry is 23, rest are this one, and IDM is the one which will design and make the chip and the package. So all these three units are done by the IDM, and it PE ratio is around 15.8. The examples of this is Hynix and Intel. You will observe that the fabless semiconductor companies are these companies: Apple, Nvidia, Samsung, NXP, Qualcomm, Intel, and Broadcom, and other companies. And manufacturing companies are TSMC mainly, and the global foundries UMC, SMIC, and Samsung. And if you observe that these are the semiconductor equipment suppliers, that means like those companies which will make tools for the foundry. for photolithography, ion implantation, etching, all these things. They are applied materials, ASML, LAM, and TEL, KLA10 core, all these things. And aside to that, these are the EDA companies, these ones which will make the tools for the fabless semiconductor companies. Mainly the Cadence, Synopsys, Xilinx, Ansys, and Keysight. And if you see their share, you will understand that the Intel, you will see the divisions. It is IDM. That means like it will make it will design and make and also make the package. So that is shown in green. And the foundry, this is mainly the Samsung partly. It will also do IDM, and TSMC is purely foundry. Like that, different segments are created. So far we have understood different components of the manufacturing, IC design and assembly that make the product specification into a realizable packaged IC. And here we will look into how the IC design phase in a little bit more detail, which is what the fabless semiconductor companies will do. In the IC design phase, the fabless semiconductor companies will first figure out what should the IC do, what is the main purpose of the application. Based on that, it will convert its requirements into design specifications. For example, what should be the display size and its format that need to be supported, what is its CPU speed, memory requirements and battery requirements, like that. This high level description will be converted into the next stage, wherein the design architecture will convert it into different components, how they need to be interacting, all that. Once the architecture has been figured out, that needs to be converted into another format where it needs to be converted into hardware description language, and you will be converting this architecture into slightly lower level. For that, Verilog tool will help, and it is written in Verilog code. So this Verilog code will be checked through Verilog simulators and then ensured that the desired functionality will be achieved. Yeah, the design data which is obtained in Verilog HDL at a very high level need to be converted into specific process node depending upon the time and the cost, need to be made into a realizable format which will be sent to manufacturing. So for that, at different times, different process nodes have been selected. 45 nanometer, 32 nanometer, 22 nanometer, like that, 10 nanometer and all, and different process nodes have been selected. So this gives the flexibility for cramming millions and billions of transistors into small area. So that is the main reason why smaller process geometries are preferred, and the speeds also will be very high at smaller process geometries. And to realize the higher level design information into a realizable data which is ready for manufacturing, there are different steps need to be taken through. That means like it needs to be converted into specific libraries associated with the different process node. Assume that we take 32 nanometer process node, then the design data need to be converted into that specific realizable IP. Then it needs to be placed and it needs to be taken through and routing, and then it needs to be ensured that timing wise and manufacturability wise it is correct, and the functionality is achieved. That needs to be ensured. Once all these things have been ensured, for that we need different EDA tools that I have described earlier, and these are the different companies which will help in bringing the design specifications into a realizable data format. So these companies, Cadence, Synopsys, and these companies will provide the electronic design automation tools to bring the high-level design data into a realizable data in specific process node. But still, this is not a physical data. This is still a digital data. Okay. However, this is fit for manufacturing. Yeah, using the IC design flow specified earlier and using the EDA tools, the high-level design data will be converted into realizable uh, gates form based on a specific process node, for example 32 nanometers, like that. Then that will be converted further into the lower level design format, which is called layout. So here now the actual manufacturable content will be created. So when this format it has been created, you will understand that this design data should have been timing wise, functionality wise, should be consistent with the higher level design specifications and the need. So if you see the zoomed in data of this part, then you will know that there are different transistors in this small part, which will have one PMOS and NMOS design that basically constitutes a CMOS design. So this is called an inverter gate. So you will understand that the gate length is this small thing, that is 28 nanometer or 32 nanometer, based on the specific process node we are talking here. So thus we will understand that smaller the process geometry, smaller will be the gate length, and hence the associated uh, uh, standard cell height. Yeah, so based on that you will understand that the design sizes will also reduce further, and the speeds also will be higher in smaller process geometries. And 28 nanometer uh, means it is closer to 2500 hair thicknesses. Okay, so that means like that much small is the geometry we are talking here. This is nanometers. Okay, so this is how small is the process node we are talking about. Yeah, this is end of part 1 on brief analysis on what it takes to make a semiconductor fab in India. Thank you for watching, and if you are interested, please watch the next part where more information on semiconductor manufacturing fab is specified. Thank you.